supersymmetry in its simplest guise. It's about spin, so we have a little cartoon here of spinning protons or electrons or whatever your favorite spinning particle is. And I like to point out to people who say, well, SUSY hasn't been found. Well, some of us never expected it to be found at the LHC. In 2006, I wrote this paper where I said that explicitly. So there were lots of people who thought they were going to find it. I wasn't surprised they did not. Let me move fast here. So Maxwell teaches us that this thing called helicity exists for the photon, and that's a really cool thing to know about. It comes out of the equations. And so photon helicity is for the photon what spin is to an electron. That's the picture I want you to hold in your mind. So you can actually see spin classically by looking at wave solutions. And now we come to Albert Einstein, this great work of that he completed in 1915. By the way, Mapp's book on Eddington and what have you, I'm very familiar with. It's one of the competitors' books. But I disagree with the conclusion that it was the politics that drove Eddington to do that. But that's the premise of that book. You can read the evidence there and make up your minds for yourselves. You're all scientists. But anyhow, in 1959, Einstein wrote this beautiful equation, which in one line seems to be able to capture the history of our universe. He did it, of course, in several different phases. This term was first not there. Then he put it there because he wanted a static universe. And then when Hubble found the expanding universe, he took it out of the equations. And then about 20 years ago, we put it back. But we put it back with opposite the sign that Einstein had because we found out we live in an accelerating universe. And for people like me, it's all about gauge theory. So we have these things we call covariant derivatives. That's what you see, this del. We calculate the commutative covariant derivative that gives us the curvature. And we can look for explicit expressions. And in particular, you can look for the wave solutions to those things. And they turn out looking like this. This is the analog of a circularly polarized gravitational wave. It has the two modes that you see there. And I borrowed those images from Stan Whitcomb of the LIGO collaboration in Caltech. One of the advantages of knowing Einstein's theory is it tells you about the universe, about its evolution, about its history, and about us. I like to tell people one of the things I think coolest about this universe is it took its own baby picture at 380,000 years old. It's called the cosmic microwave background. We found out about it starting in the 60s. We have satellites. And so what I really want to tell you today is something really weird. So about 3 years ago, I was being recruited to move from my then home University of Maryland to Brown University. And I had this idea that, based on a paper of Arkani Hamed and Maldacena, that string theory might actually be able to leave signals on the cosmic microwave background. And that's the topic of this talk. So let me tell you a little bit about string theory. It's about filaments. They oscillate. There are an infinite number of them that correspond to an infinite number of particle states and, more importantly, particle spins. So unlike cutting off at the 2 that we have for the graviton, it goes on forever. In string theory, we can do various things that make them go right movers or left movers. And by superimposing these various kinds of oscillations, we think we get the particles in the standard model. So when you're a particle physicist, you learn some tricks. And one of the tricks that we learn is how to use the decay products of a collision to study the particle that gives rise to the collision. In this case, I'm showing you the cartoon about the decay of the Higgs boson into 2 Ws. So this trick, it turns out, can be applied to an idea having to do with the cosmic microwave background. I hope some of you probably study Gaussianity and non-Gaussianity. You know that the cosmic microwave background is incredibly Gaussian. But in fact, there have been speculations that if we measure at a sufficiently fine level, we will find signs of non-Gaussianity. And for people like me, the excitement about that is that the non-Gaussianity may be a signal that you can use the cosmic microwave background as a particle detector. And so the idea is these extra states of the string, could they affect the non-Gaussianity that you would measure in the cosmic microwave background? And so, you learned some atomic physics a long time ago, so you've seen these things. And you've seen these pictures about orbitals and what have you. And the really weird thing of the suggestion by Arkani Hamed and Maldacena was that if you look at a particular kind of collision in the presence of the early universe, when these heavy states would be there, look at a glancing collision of 2 heavy particles with the with the scale factor of the universe, and it could leave signals on that scale factor of the universe if they're glancing view blows. And this collision, curiously enough, is characterized by the associated Legendre polynomials. So the same mathematics that you learned in quantum mechanics that tells you about orbitals, according to this suggestion, will also be a possible mode to detect heavy states of string theory coming from the CMB. There are a few technical things you have to worry about. I'm not going to bother with the details, but supersymmetry we expect to be broken. We've studied equations about how that can be done. And this is the punchline. 3-point correlators of non-Gaussianity in the CMB, calculated in this limit of glancing blows where the two heavy particles barely collide, so a small exchange of momentum, those collisions are characterized by associated Legendre polynomials. That's the assertion. And there's a whole, I don't know, again, how familiar people are with non-Gaussianity, but there's been a whole sort of industry built up around using the Gaussianity of the CMB, and so therefore you can think about it as a totally stochastic system, to actually use that stochasticity to then look at a set of quantities that look like particle physics from people like me, where you have in-out states. Here it's what's called in-in states. But the whole machinery of Wick expansions and all that stuff that I learned when I was about the age of the young people in this room, that now comes roaring back into the discussion, but now with regard to non-Gaussianity. So I and my collaborators, after I saw this idea of Kani Hamed and Mount Sena, I thought, well, gee, they're going to next tell me that, yeah, this is going to be a particle detector for the high mass states in strings. And by high masses, by the way, remember I showed you those oscillating pictures? Well, as far as those are accurate pictures of how string theories work, it means the masses have scales up to infinity. And in particular, very, very large masses, well beyond Planck mass. So you have to look for very special regions of the equations that allow you to say, well, gee, it can't be too heavy, because if it's too heavy, this approximation wouldn't work. But if you assume that that does, you can then say there must be an effective action. And so effective actions are tools that we in particle physics have been using since the 50s. The old description of the weak interaction from Fermi was an effective action. It ultimately led to the discovery of the W, Z particles. So we can bring that same machinery now back forward again. And what we find is that there's a mechanism. And the reason this title is a speculation is we don't know about amplification. So we don't know how strong these signals are. We're not guaranteeing that when you get to the Webb, satellite, you're going to immediately see these signals. But we have found a mechanism by which string theory can leave signatures on the CMB. And as I said, the mechanism works in a very interesting way. If you do no supersymmetry, you get a scattering, essentially something that looks like a scattering amplitude characterized by these associated Legendre polynomials. With supersymmetry, what you find out is you need a detector that does the following. It fixes a mass scale, it fixes energy, and then you need to be able to scan in different spins. And when you do that, what you'll find out is that there's this characteristic straight doubling. So you start at a given spin, you go to half a unit higher, and then 1/2 a unit, start with a given spin, come down half a unit, come down half a unit more, and you'll find this characteristic 3-channel signal where the signal goes up by a factor of 2 in the middle. So that, I guess this is like the Gong Show, and I did hear that sound, so I'm going to quit right here. We don't have, sure, we have no guarantee, and that's why this is called a speculation. Nature. So the point is that nature would have to be kind to us for this to actually be one day, to be something that you could think about building a detector to find the waveforms. So for example, we haven't even figured out what waveforms look like for this. We've just proposed that this mechanism is there, And on the basis of the assumptions that we state very clearly, we can say we see this dependence on spin at a fixed mass, which is kind of it's kind of a robust signal if we get amplification, and if the mass scales are right.
Yeah, supersymmetry between bosons and fermions paints a nice picture, but why stop there? I mean, if symmetry is what we're going for, why not speculate other symmetries between, I don't know, leptons, fermions, and also why do we have? But now we've gotten rid of some of the minimally supersymmetric.
Absolutely.
The standard model, but what would you think would be the preferred amount of symmetry that we would be tending to, or what can you make more precise the criterion that makes symmetry favorable?
So let me first of all back up to something you said, which is symmetry between leptons. We already have what's called quark-lepton symmetry in the standard model. That's why there are 3 families of leptons that go along with every family of quarks. So we do see some extra symmetries of that already. Why stop at supersymmetry? Well, supersymmetry actually has some very peculiar properties that are not things that are generally studied, but they're the kinds of things that drove people like me to enter the field when I was your age. And these properties have to do with vacuum stability. It turns out that if you write the conventional relativistic quantum field theory, you have a set of coupling constants in it. Those coupling constants may have different values, but for whatever reason you might say, I want this coupling constant to be related to that coupling constant by some ratio or some formula. It turns out that in the standard relativistic quantum field theory, in order to maintain that relationship, you will have to, when you do renormalization, it will typically drive the system away from whatever constraints you put on those coupling constants. It turns out supersymmetry is the only relativistic field theory where we have ever discovered where this phenomenon does not happen. And so we think there's something very special about it. But it has nothing to do with dark matter and all this stuff that you guys know about.
Can you tell us what level of non-Gaussianity you would predict in this speculation? And you mentioned using the CMB as a method for teasing out this non-Gaussianity. Is there any reason why you couldn't do it from large-scale structure measurements?
Gary, I haven't actually thought about that, but if you can get accurate measure of non-Gaussianity from large-scale measurements, if you can do better, I need to talk to you.
What level of non-Gaussianity?
And that's a question I don't know. I'm sorry, I should have said that one I don't know. But I'd like to talk to you about this because we're looking for other sorts of phenomenology that might allow people to go look for this stuff. Right.
And the universe is 3-dimensional. So by probing structure in the 3 dimensions, tighter constraints on the early universe.
Yes.
That's exactly the reason.
Yeah. No, as I said, I'll be very happy to talk to you, Gary, about that. So is my 30 minutes up?
So actually, being on this question, I feel like that they would also suggest that the dimension must need to be mass above the Hubble constant.
Yes.
So in fact, you don't need to go to infinity.
No. In fact, In fact, in our paper where we actually talk about the speculation, we say that you want things to be slightly under the Hubble mass in order to have this mechanism actually have some possibility of actually working. So, but you're exactly right. Sure. I thought I only had 10 minutes here.
If the fermion always come in groups, how can you tell if you see some signatures, how can you tell it's definitely a fermion?
Well, so the idea is, how do we do this in particle experiments? The point is that you essentially look at things that are like scattering amplitudes, and scattering amplitudes typically have, when you look at the angular dependence of a scattering amplitude, they typically are controlled by the spin of the object that's actually causing the scattering. So here, the idea would be that you would look at the non-Gaussianity to see if you can see that same dependence. I've actually pointed it out to you here because it is that parameter S that I had in the associated Legendre polynomials. But with regard to this mechanism, you will be able to detect the difference. Because you're right, it behaves as a boson, but the point is that this particular mathematical, this is like a scattering amplitude. You would see this effect at this spin. You can actually look at it there. Oh, okay. Is there anybody else? Because I mean, Gary, Shingdong, I mean.
Turns out you will find many more people that will benefit from conversation in this building than in the 50 Jefferson.
Well, you know, except for my daughter, I would agree with you.
That's right. I take that.
Okay. Okay, so am I done? Thank you. What happened to the... I'll get this. Thank you. Thank you. All right, great. At least for me, the ITC lunches are kind of the highlight of the week, and so it's nice to be able... It's not on. Now on, or? No. You have to do something. Right now? Okay. All right, I'm going to talk about the stability and solution of the time-dependent Bondi-Parker flow. So the Bondi and Parker in the 50s came up with the solution for two different phenomena in astrophysics. One is accretion onto a constant point mass, and the other a pressure-driven stellar wind. And they both have the same mathematical solution, even though they're quite different phenomena, which on one hand is surprising, but on the other hand, all there is the Euler equation for fluid dynamics. And so that's this equation here. So there's an advective term. This is the pressure gradient and the gravitational force in units of gm over the sound speed squared. So what Bondi did was he says, all right, so he solves for the steady state solution and substituting for the density with the continuity equation, you get one equation for velocity and position. You integrate that and you get a steady state solution. And this equation has proven to be enormously useful in astronomy, and one reason is because of the existence of a transonic critical point. So where the velocity goes to 1, then in the non-dimensional units, x has to be equal to 1/2. So that's, this is the Bondi accretion flow here. This is the outward Parker wind here. The steady state solutions have this constant of integration, which for different values gives you a subsonic flows, transonic or supersonic. But that transonic critical point gives you a natural boundary condition for whatever problem you're working with. So you could be going from black holes to brown dwarfs, and you don't really have to specify the conditions on the boundaries for the problem. Now, all of this sort of rests on the assumption that, which I sort of turn into questions, you know, say for example, whether the time-dependent flows will evolve to the steady-state solution, that the steady-state solution is stable, and given some initial values, which in the family of steady-state solutions will the flow evolve toward, in particular under what conditions a transonic flow will develop. These questions have been addressed over the literature, including some arguments by Bondi, and they haven't been convincing. All right. So after looking at this for perhaps an embarrassingly long period of time, I said, well, that steady-state solution is the Lagrangian for that equation of motion. So there's the kinetic energy term, the potential energy term, and these two terms are the internal energy of the gas, which you need for a Lagrangian for a fluid. All right, so that essentially solves the first question. So
that Lagrangian, or that steady state is the Lagrangian. That's the solution of least or stationary action toward which the time-dependent flows will evolve. And then that allows an answer to the stability in a fairly straightforward way. So in the calculus of variations, the first variation gives you the solution of stationary action. The second gives you the stability. And so just working through that, we can say that the isothermal and adiabatic flows are stable, and other equations of state are indeterminate. Now, it's a consequence of the non-canonical Hamiltonian of a fluid system that those are the two outcomes of the stability analysis. In a canonical system, you would get typically stable and unstable. All right. So that takes care of the first two questions. Now we say, what about the solution of the time-dependent flows itself? And so the way I addressed this was, so I start with this partial differential equation, and then I use the method of characteristics to break it down into two ordinary differential equations. So here, x is going to be a function of time rather than an independent coordinate. And the essence of this method is that this coordinate x is going to follow along some trajectory, which is the coefficient of the advective term. So x is going to follow the fluid along in some Lagrangian sense, and then along that trajectory, you can integrate the velocity and get the velocity as a function of time and position. Now, whether this, you can do this for any equation that's first order, and these differentials will give you this pair of ODEs, and whether that helps or not kind of depends on the equation. But the big advantage in this problem is that normally you would solve this PDE as a boundary value problem, and this turns it into an initial value problem. And we'll see in a minute that the boundary values for this Bondi-Parker solution are really problematic. All right, so let's just look at some examples. So here's an accretion flow, and the red line is my initial velocity. So I start off from some very low initial velocity, then I let the system evolve, and this fluid here gets swept up very quickly into approximate free fall, and the whole solution begins to approach the Bondi accretion solution, the transonic solution. And here's the same evolution for a wind. So in this case, I should say I'm plotting the absolute value here, so the negative velocities are top of the screen. For the wind here, you start from a low velocity, and again it gets swept up into this Parker wind. And in this particular example, as the flow becomes supersonic and impacts these lower velocities from the initial conditions, then you get a shock, right? Now you could also look at the purely subsonic flows. So here's an example of one that I have two subsonic trajectories plotted here. So I transition from one to the other smoothly, so I don't give the Runcuda stepper the EBGBs. And then the evolution is the flow wants to evolve down onto this lower steady state solution. And similarly, if you just put a sinusoidal perturbation on one steady state solution, since there's no dissipation in the system, it will just ring happily for eternity, barring dispersion. All right, so what about these, why do these flows become transonic and these don't? All right, so if I divide this diagram up into 4 quadrants, and being an astronomer, I could call them type 1, type 2, type 3, type 4. But wouldn't really be the point. So looking at these trajectories, you'd say that the trajectories, it's not obvious in this plot, but if I have put the third dimension in, so I have time, a 3-dimensional plot of time, velocity, and position, then looking at the characteristics or the tracks of x versus t, I'll find that the solutions will not cross these boundaries. So if you're inside one of these boundaries, then you're going to stay there, and the best you can do is get up to you could get to the boundary of that region, right? So most realistic initial conditions, say for example a constant, will cross at least 2 or 3 of those boundaries, because both of these solutions on both ends go to the velocities go between 0 and infinity asymptotically. So any constant value is going to cross one of those boundaries. So that's the condition for a transonic flow. On physical grounds, you could say, well, this material gets swept up into free fall, it drags this stuff here, and then it gets locked in on that effective boundary condition at the transonic point. And similarly with this flow. Now, so here, in order to get a set of initial values that don't cross the boundary, you have to construct them in a special way. So they have to go to 0, say, asymptotically faster than the transonic solution. But that's not that difficult because we already know that these steady-state subsonic trajectories do that. So if I just pick my examples, then I've satisfied that condition. Okay, so that essentially answers those 4 questions, and that sort of puts this framework for using the Bondi-Parker flows on a sounder footing. I don't mean to raise the alarm there because there's a huge amount of experience with numerical simulations, and everybody agrees that the transonic solutions are developed under a wide range of initial conditions, and that they're rock solid stable. But there's a lot of disagreement about the other solutions, the subsonic and supersonic. Okay, so then we use the method of characteristics to get a solution for the time-dependent flows and develop the conditions for the transonic solutions. Yeah.
Maybe the future edition of the SUSY aerodynamics. The Parker solution obviously can be seen in the solar wind, right?
Yes.
In a way, it's reflected there. Have we ever observed Bondi accretion? Is there data to support it?
Well, the Bondi and the Parker solution, I think, are most valuable if one wants to study pressure-related phenomena in a context of accretion flow or a wind. The major problem is that they don't have rotation. Right? So most astrophysical systems have rotation. However, just from my own experience, we have successfully used the Bondi accretion solution for modeling accretion flows in high-mass stars. And somewhat curiously, we've also modeled the same stars with this model from Ulrich of ballistic trajectories, which has no gas pressure but has angular momentum. And the reason is because they don't spin much. Right? So I would say approximately yes.
Could you think of this like a causality argument that information isn't able to propagate upstream, and so it doesn't it inhibits your ability to develop instabilities?
Well, I certainly haven't thought of it that way. That's an interesting question. Probably not, because we have these subsonic flows, and so what you say is true. In a supersonic flow, the pressure gradient won't go upstream, but I don't think that's say, for example, in the Bondi accretion solution, the solution gets swept up into free fall. That really doesn't have anything to do with the pressure, right? And then it locks in on that transonic critical point. And then on the other side is largely hydrostatic. And so there, if the flow is coming in too fast, the pressure and density build up, and it slows the flow down to get through the transonic point. So, no, I guess not. Now that you mention it. Yeah. Okay, I'm leaving it on for you.
It is on, sort of. Okay, hi everyone. Oh, you see my messy background, sorry. All the papers I'm supposed to read. It's nice to see you again. Hopefully you won't be too sick of me. I promise this will only be 10 minutes, so limited exposure. So it's a very big break from everything we've talked about before. I should admit I'm an observer. Okay, so I'm not a theorist, but I do work with theorists, and I call some of them friends. So today I just wanted to present some observational results that two of my students have been working on over the last couple of years. And as with all of my talks, I kind of like to just always preface with a question, which is, points if you can tell me what this image is, not what it is, which system it is. Got the Abel part right. Abel, galaxy cluster.
The universe.
The universe, excellent. Always a good answer. I'll let you guys ponder that for a while. So yeah, it's a galaxy cluster. You can recognize that it's obviously HST imaging because of the arcs. But I'm not focusing on the arcs in this talk. I really want to focus on the galaxies themselves. And you can see that they're all reddish orange, which means that they're old stars. And so the question for me is when, where and when do all these stars actually form? This is a fairly low redshift system, so most of the actions already happen. And so what we need to do then is to really push to high redshift to the distant universe so we can go back in time and try to look at the progenitors of systems like this to really try to put together a picture of how and when these galaxies formed their stars and why they stopped. Right? So the Milky Way still gets to form stars, but why do these galaxies? Why don't they? And so I like to, going from that to here, it's the Andromeda galaxy, our nearest massive neighbor. And so the idea here is, you look at the Andromeda, you see it has a bulge, it has a disk, and it has stars and gas and things. So the question is, which form first? The bulge, it's like a chicken and egg, bulge or disk. Do the bulge form first? Do they form together, disk first? And so the idea is that with the observations, we can hopefully try to piece together information that allows us to test formation models that then allow us to connect across all of these different cosmic epochs. Because as an observer, of course, I only get to see one snapshot at one point in time, but like a photo album, you hopefully can connect many pictures all the way from being a baby all the way to pensioner, such that you can get a complete picture of this galaxy evolution. And so I go from a nice picture of Andromeda to these. These are the best imaging that you can get these days. This is with the Hubble Space Telescope of galaxies at about redshift of 2. Not particularly impressive. That's okay. I understand. But this is to demonstrate how hard it is to do this at high redshift, right? So you have the beautiful detail of the Andromeda galaxy, and now I have smudges. So I try to use information of these smudges taken with the Hubble Space Telescope and combine it with ground-based observatories like Keck and the VLT in Magellan with spectroscopy to really figure out what their compositions and kinematics are. So what we have here on the x-axis is stellar mass versus star formation. And the left panel, there are lots of dots. All you need to notice is that they all fall on a kind of a diagonal, and that the blue dots and the red dots aren't really that different. It just means that the cluster galaxies and the field galaxies, galaxies that are in overdense environments versus galaxies that are in underdense or more typical environments, don't seem to be very different in the high redshift universe. This is a system at redshift of 2. So what I've done now is on the left-hand side, I've taken the galaxies that are on the upper edge of that envelope. Those are things that are forming lots and lots of stars for their given stellar mass, right? So basically, at, say, stellar mass of this, the purple squares are forming more stars per unit mass than the yellow. It's hard to say color and shape at the same time. Yellow triangles do. And so if we want to look at these purple squares and think of those as basically starbursts, the question is that where do those stars actually form? So just focusing on those objects, what we see here hopefully is that you have stellar mass versus now size. And you can hopefully see that most of the purple squares actually lie low on this plot. And so that just means that they're smaller for their given stellar mass compared to their colleagues. So that new star formation is actually happening in the core. And so that's consistent with this idea of a concentrated star formation. It's particular with clusters because clusters look more elliptical, they look more bulge-like. And just from the imaging alone, you can see that the star formation actually is fairly concentrated. But now we see that these things are starburst, the ones that are starbursts are forming most of their stars in the core. So then just a quick switch to another way of looking at these systems. This is work led by my PhD student, Anisha. And she's looking at the electron density. And I know this is a very not particular. I think I win the bet for ugliest figure here. So the idea here is you have Sloan, you have stellar mass once again on the x-axis, and on the y-axis you have electron density. We get that by measuring line ratios, just atomic physics. Sloan is bimodal, that's why you get this batch here. This is just really, ignore that. We're looking at these things up here, which are star forming. And so you see a lot of different colored plots or points, which probably are not very reassuring. So let me make it simpler. I don't know if that helps. But essentially what you see here is that these points lie above where Sloan is. And so that means that, and this is something that has been observed by other studies, which is simply that the electron density is increasing at higher redshift. So these points are all above a redshift of 1, basically between 1 and 1.5. So all of these points lie above where Sloan is. So the electron density, in other words, the interstellar medium, is evolving such that electron density does increase with redshift. And for the first time, we've also now measured it in a cluster environment. And we show that the red points really aren't that different from the other points. To be fair, I was honest. I showed you the scatter. But at least within these limited observations, which once again are very difficult to obtain, we don't really see any evidence for any difference between, say, the cluster environment versus the field environment. And Anisha's paper was just accepted, the first lead author paper, and it was just on the archive last week. So you can see that. I didn't have a chance to talk about Leah's work. She was graduated last year, but if you want to talk about dark matter or not, you can look at her series of papers where she looked at the dark matter using galaxy kinematics of cluster galaxies versus a field around a redshift of 2. This is a figure from one of her plots. And so I think the takeaway message is that at least at redshift of 2 or so, we don't really see any strong dependence on environment. And you're probably thinking, well, that doesn't seem like a good thing. For me, that's great, because that basically tells me that all the mechanisms that make galaxies and clusters different from galaxies like our own Milky Way really start to come into play below redshift of 2. And so now we can really focus on this epoch, most likely between redshift of 1/2 and 2, to really try to understand the physical mechanisms that are causing the galaxies in the overdense environments to quench earlier. And so this is actually a feasible redshift range for those of us who do this type of work, which is very exciting. And so these are published in a series of papers, Z-Fire papers, on, as I said, by Anisha, collaborator Glenn Klapsack, myself, and of course my student, Leah, no longer student, she's a York Fellow up in Toronto. So, thank you.
Another way to think of clusters is an overdense environment in the universe where, if you just separate it from the rest, it's just like being in omega greater than
Yes.
one universe. So the clock is ticking faster.
Yes,
All the
absolutely.
evolution that you see elsewhere in the universe occurred earlier.
Absolutely.
That's consistent with what you're showing. Now, do you have any data from the Svinazadovich or X-ray on this?
Yeah, so we do have X-ray data for these fields. The X-ray data are relatively limited. I hope I don't offend anyone. Simply because we're working at high redshift, redshift of 2. And in terms of like Svinyaev-Zeldovich effect, there has been X-ray detection of the ICM up to, I think, 1.8 or 2, but that was like one object. And so in terms of point sources, we checked. There's actually a paper I did talk about that, on the incidence of AGN that also use X-ray detection to see if they increase in clusters at higher redshift. The problem is that we're really dealing with low number statistics, and so we find tentative evidence of that, but it's really, the error bars are so large. In terms of the acceleration, that's 100%, the mentality, the perspective that we had going in. The interesting thing is, as I said, at redshift 2, it doesn't seem like there's any difference yet. So whatever that acceleration happens, it has to happen below redshift of 2, and it has to happen really fast. So it's a combination likely of many mechanisms, quenching, heating of the gas, etc. But now we can really try to develop experiments in a way that allows us to isolate the relative contributions of those different types of mechanisms.
Any other questions? Yes, Anna?
So among those very fast or highly star-forming galaxies, are there any a large fraction of mergers?
Oh, yeah. So my undergraduate, Courtney Watson, who actually just started grad school across the water, she did look into the merger fraction, and she looked at this cluster, but then also a couple of other clusters, further cluster systems around redshift 1.5 to 2. And we actually do find a higher incidence of mergers, or at least amongst what we consider minor major mergers. And I think it's at least a factor of, I'm going to make up a number. It's published, so whatever that number is, I think it's 3 or it's higher in the cluster. It's higher in the cluster, which makes sense because actually in my past, I did write a paper on the higher merger fraction, but this is one of the first works where we really push this up to redshift of 2. Having said that, the caveat being we don't have enough leverage on the cluster side to really measure this robustly because there are not that many clusters. It requires spectroscopic confirmation, all of these other things that really limit our ability to measure it accurately. So part of that process will be to hopefully observe more clusters at higher, continue to absorb more than just a handful of clusters at high redshift.
Thank you very much.
Thanks.
Thanks. Where'd the dongle go? Here it is.
Oh yeah, sorry. That was kind of a very, very brief overview. So if you go to zFire, just do zFire in my name, there's a web page, and we have all the papers, and the 2 questions in particular that I focus on. Oh, that one. Okay, fine. It's Abel 1689.
All right, so I'm Angelo Ricarte. I'm a postdoc at the ITC who started in September. I spend half of my time working with Event Horizon Telescope stuff with Ramesh Narayan, and the other half of my time working on much larger galactic or cosmological scales. It's those sets of scales that I'll be telling you about today, work that I've been doing on the Romulus cosmological simulations run by Michael Tremmel. So in our current picture of galaxy evolution, black holes and their galaxies are linked. Galaxies provide fuel, the gas, to grow a black hole and make it shine as an AGN, and in return, the black holes return feedback in the forms of winds, jets, or just thermal energy, as is implemented in this archetypical case. Here we have a gas-rich major merger, which funnels gas to the centers of the galaxies to feed black holes, and in a moment you'll see them turn on and release feedback energy to stop their own growth and quench the growth of the galaxy overall. At redshift of 0, we see these relationships between black hole masses and galaxy scale stellar properties, like this one, the M-sigma relation, where the mass of the black hole goes as the velocity dispersion of the bulge component of the galaxy to the 5th power. And it's possible that this is the result of a causal process like fueling or feedback. And yet this is redshift 0. There are still a lot of open questions in terms of how black holes and galaxies get to these relations. In the early universe, both black hole masses and stellar masses are a lot smaller, And so we'd like to know how you get from one side of this plot to the other. And for one possibility is that the galaxies grow first, and then the black holes need to catch up. And this is actually a picture that is seen in several hydrodynamical codes, where in this picture, gas that is trying to pile into the center of the galaxy and fuel a black hole instead gets blown away by supernova feedback until the galaxy has a deep enough potential to hang on to that gas. Alternatively, maybe at least sometimes the black holes grow first and then the galaxy needs to catch up. And one of the reasons why one might favor this picture is because at redshift of 6, we see these quasars that already have 10 to the 9 solar masses in their black holes when the galaxy is only a gigayear old. It's hard for anyone to grow those. It's a major unsolved problem. Even harder if you need to wait for the galaxy to catch up. And then, of course, perhaps you can have this scenario in the middle, coeval growth. The right picture may very well depend on the stellar mass, environment, or redshift. And one of the best ways to study this problem is to run a large cosmological simulation and evolve your black holes and galaxies self-consistently. The ones that I analyze are the Romulus simulations run by Michael Tremmel. And he likes to advertise the great black hole recipes that he uses. In particular, seeding is based on local properties rather than, say, a halo mass threshold. And the dynamical friction onto black holes is corrected such that you can make good predictions for the wandering population. But relevant to the work I'm going to be showing you today, accretion is Bondi modified a little bit for rotational support. Feedback is purely thermal. And Romulus has both a field, which is Romulus 25, this 25 megaparsec cube volume, and a zoom in on a cluster, kind of smallish cluster, 10 to the 14 solar masses, virial mass, and that's Romulus C. And so we can compare how black holes grow in the field versus in the cluster. And in a paper that I finished over the summer, the main result was that black holes and galaxies co-evolve. This is Romulus 25. You're looking at 6 different redshift snapshots here. And this is a plot of black hole accretion rate versus star formation rate, color-coded by the stellar mass, going from the dwarf galaxies in red up to the more massive galaxies in blue. And you could see this nice linear correlation that seems to be true for all stellar masses and all redshifts. That gray band is Mullaney et al. 2012 observed relation at redshift of 1, where he coined the hidden AGN main sequence. And you can see that that same relation actually holds from redshift of 0 all the way to 4. But there are a couple things that I did to make this so clean. So first, I averaged over a long time. This is 300 million years. And second, I only included the star-forming galaxies. The quenched ones buck the trends in ways that I'll get back to later in the talk. Now, this was the field, Romulus 25. And if we look at the cluster, you see that it's actually exactly the same. So there's no dependence on the environment either. At redshift of 0, there are many fewer points on the plot. That's because, again, I only include the star-forming galaxies. The galaxy likes to quench, or the cluster quenches galaxies. But as long as you have a star-forming galaxy, it doesn't matter what stellar mass, redshift, or environment you're in, the black hole accretion rate follows the star formation rate in these simulations. In a more recent paper, we're looking at the connection between ram pressure stripping and AGN. So here's a galaxy that is a type of galaxy called a jellyfish galaxy. You can use your imagination to figure out why. And this is falling into a dense intracluster medium and facing a headwind. And this ram pressure, going as rho v squared, is stripping away the gas, working from the outside in until you get to this kind of late stage where only the inner parts of the galaxy have gas that are still being stripped by this ram pressure stripping process. And this is an important quenching process in dense environments that people are trying to better understand. And interestingly, in this recent study by the GASP collaboration, they were looking at a sample of jellyfish galaxies and found that 5 out of 7 had signatures of AGN. This is one example. On the left side, we have the molecular gas. You could see there's a hole of cold gas at the center. And at the same time, the spectroscopy shows that there are signatures of AGN in the center compared to a more star-forming radiation field on the outskirts, which is highly suggestive of AGN feedback in action in this jellyfish galaxy. The thing is, though, that there didn't exist any theoretical simulations to compare this to. Although ram pressure stripping has been studied numerically for a while, people just haven't put a black hole in those simulations. It was not thought to be an important part of the process. Luckily, Romulus C naturally produces jellyfish galaxies, and black holes are already in them, and so we could see what happens. Here are 3 examples of jellyfish galaxies in Romulus C, and in the middle row, I'm plotting specific growth rates for the stars in blue, the black holes in red, and then the incident ram pressure as that dashed orange line. And you can see that at the end of these galaxies' lives, when they stop forming stars, there's an increase in the black hole accretion rate at the same time that you have a peak in the incident ram pressure. Not exactly aligned. This one's a little before. This one's a bit after. And then this third one's my favorite galaxy in the entire Romulus simulation, where every time it passes Perry-Center, every 2 billion years, the AGN starts up again at a modest Eddington ratio. On the bottom, these are masses, gas masses in gray, which plummets after one orbit, while the stellar mass isn't too affected, which is, again, telling you that this is really ram pressure, not something like tidal stripping, which would also remove the stars. So here is a plot where I'm now showing all of the galaxies in Romulus C, and I've aligned all of their black hole accretion rates and star formation rates at Perry-Center, and ask how elevated is it compared to some baseline values, which I define as being 0.5 to 1 gigayear prior. And as I play this movie, you could see this enhancement of about a factor of 2, but it varies a lot between these galaxies. They're all on different orbits, so many have much stronger peak ram pressures than others. In the dwarf galaxy regime, you see things die more rapidly. That's because they have less gas and also a weaker gravitational potential well, so ram pressure can completely remove the gas much more quickly. And Romulus C also provides us with this interesting case study. So we've got 2 similar galaxies here. Both of them are 10 to the 10.5 solar masses and stars. And they also have very similar orbits. These dashed lines show the ram pressure over time, peaking and having very similar widths. But the thing is, one of them has a black hole and the other one does not. And the one that does not have a black hole, as it passes Perry-Center, this is the specific star formation rate. You've got a little peak, but it takes many gig-years for it to quench entirely. In contrast, the one that does have a black hole has a peak in the star formation rate, but then everything plummets when you've got this peak in the black hole activity at the same time. And in the top row, these temperature and velocity maps kind of show us what happened here. In the case where you do have a black hole, it started accreting, and then the thermal AGN feedback heated up the gas at the center and started driving a wind of up to about 300 kilometers per second. And so I think this, if you turned it around, would probably look a lot like this galaxy that I showed you before, which had that hole of cold gas at the center, and in fact also has an outflow of about the same speed. So in conclusion, in these Romulus simulations, we see that black holes and their host galaxies co-evolve independent of stellar mass, redshift, or environment. In the cluster, we show for the first time, in theory, the link between ram pressure stripping and AGN in a hydrodynamical simulation. And there may be some synergy there in terms of them working together to quench galaxies. But more studies are going to be needed to validate these results, better understand them with other subgrid models and techniques. I bet that similar results exist in the TNG and Sea Eagle simulations. It'd be interesting to see how they look. And just more controlled, real case studies would also be very useful to try and disentangle all these effects that are happening at the same time in a galaxy cluster. So thank you, and I'll take questions. Well, so you mean for ram pressure? It doesn't feel the ram pressure. It's just. Right. That's not something that I've looked into.
If the gas is stripped away, so what is feeding black holes?
Yeah, so this is at the very end of the stripping process where you still have this tiny nugget of gas. So it's that last piece of gas, we think, that is getting compressed. And then after that, the combination of AGN feedback and ram pressure stripping gets rid of all the gas entirely, and then there's nothing. Both the star formation rate and the black hole accretion rate are 0. Yeah. Sure.
So, kind of it's actually a similar question, but you showed that example where it periodically turns on and off, the AGN.
Mm-hmm.
So if you remove the gas, how can it turn on?
Yeah, that one I think is that's the most massive galaxy of the 3 that I showed. That one, there's a tiny bit of gas that sticks around in the center of the galaxy, and that's plausible in the deepest parts of the most massive galaxies. And for some reason, it isn't completely removed. It'll be interesting to know if that stands up at higher resolution, different subgrid physics, etc.
It's rather like a broad question, but just to have an idea, which is the range of Eddington values that you observe in different cases?
So it varies. So in Romulus, the average Eddington ratios don't actually get very high ever. Usually they're around 10 to the minus 2. They only get higher than that on very short timescales. And here I've even smoothed it a little bit in order for clarity. These little peaks down here are 10 to the minus 3 to 10 to the minus 2. Yeah, but I think that the jellyfish galaxies don't require very large Eddington ratios either. Mm-hmm.
Yeah, basically my question is how does your separate model, how is your separate model better than, say, other simulations?
Well, so this kind of, my point with that was that this kind of study hasn't been done in a hydro simulation that has black holes. This sort of thing has been done in like a semi-analytic model where you evolve a black hole in a galaxy cluster. I expect that you'll have similar results for Illustrious, Eagle, etc. The accretion and feedback isn't particularly special in the Romulus simulations. Seeding and dynamics maybe, but that's not relevant for this particular result.
One should also note that the dynamical time in cluster is a other gigayear.
Mm-hmm.
Usually AGNs are actually per percent per time, so 3%.
Right.
So that's why you wouldn't expect it to be more than 1% of Eddington. And if you were more than that, then the
Yeah.
value would grow dramatically.
Mm-hmm.
Okay, there are no more questions. Let's see, Angelo.
You can
Hey.
remove it first.
Thanks.
Sure.
I forgot I had this. Yeah.
I think that they just disconnected already.
Okay.
I'm sorry.
Yeah.
So actually, this is a question to show this plot, right? That was like a star formation rate
Yeah.
with and without supermassive black hole. Time from the pericenter crossing, right?
Yeah.
So the bottom line is that anytime that you get this actually pericenter crossing, you drive some AGN and then your star formation rate just drops down.
Yeah, so the star formation rate's going to die regardless of the AGN, actually. So ram pressure stripping.
That's kind of things that I want
It's
actually
just-
to fully understand.
Yeah,
first
so
of all,
in this example, though, it was
let me understand.
sure.
Let me understand. So imagine that you have like your cluster, you have a supermassive black hole around that, and in fact there are some like stellar clusters that are orbiting around supermassive black hole, right? In terms of
Yep.
like dwarf galaxy or whatever, right?
Yep.
So these are like tracers to that supermassive black hole, right? Is that true?
What do you mean
around
tracer?
that, no, like a tracer, like a kind of like orbiting objects, like heavy objects around the supermassive black hole, right? This is what you are trying to say, and you are saying
So
that
these
when
are-
you get close to the supermassive black hole, a star formation on that stellar cluster just get killed.
Okay, so there's
stripping the supermassive black hole, strip all the stars.
So the
like all
black hole
gas
is in.
from the.
So it's a galaxy cluster. You've got the big black hole and the big galaxy. I'm not
Sure.
talking about that. It's as any satellite galaxy. It could be a dwarf. Could be more Milky Way mass.
Yeah.
It has a black hole and it has gas and stars.
Okay.
As it moves into the cluster, ram pressure is going to remove the gas, not going to touch any of that other stuff.
Exactly,
It's not
because
affected.
of that central massive black
Yeah.
hole. You get out of it. Okay.
And that's understood. But at the very
Sure.
end of the galaxy's life, where ram pressure stripping has maybe made it all the way to the inside, you've got some compression, which is going to help fuel the black hole, and at the same time that it's removing gas. So it's kind of complicated
I
to
got
see
you.
the
So
signatures.
you were saying that
Yeah.
at the center of your cluster there is like a super giant black hole, and then it actually does a lot of different things. One is that it strips the gas as you get closer and closer to that central black hole, and the other one is that as you get closer,
So
the
the
black hole gets fuel, and then the black hole at the center of this little dwarf galaxy grows.
So
Is that true?
the central black hole of the entire cluster isn't doing anything in this
But
story.
it actually does the stripping, no?
No, that's just
So,
just
okay.
the atmosphere, the intercluster medium.
Oh, I see.
Yeah.
Okay,
So
but okay.
10 to the 7 Kelvin gas that's
I see.
around the entire
But
halo.
yeah, that was like. But then, what do you mean here? But I mean, this is like a time to pericenter crossing of who?
of the satellite inside the cluster. So
to the supermassive black hole, right?
to the BCG, but yeah. Mm-hmm.
Okay.
Oh, brightest cluster galaxy, the central galaxy. Yeah.
I see. So with and without black hole, right? I mean, here I see. Okay.
Yeah. So
Okay.
there was
So you see my confusion, right?
Right. So
It's
there
like,
was a
because
galaxy.
If you don't have supermassive black hole at the center of your cluster, still the stripping should be there. And still you should see some change
That's the black hole in
star
the satellite
formation.
galaxy. So there were two very similar galaxies. It's not a real case study, but one of
Okay,
them.
I'm very confused, honestly. But you should
Okay.
maybe you can just draw some pictures, right? And you see my confusion, right?
Yeah, sure.
It seems like that you are saying opposite things, actually.
Oh, no.
I mean, of course you are not saying that, but let me put it this way. So imagine that this is your super big cluster, right?
Okay.
And imagine that you have a very massive black hole here.
Yeah.
And imagine that you have a white dwarf, right? Dwarf galaxy with some central black hole.
Yep.
That is just like crossing you from this point. So tell me exactly
fine.
what you are gonna to see.
Okay.
Yeah, let's
So-
go there.